Alright, we're going to go ahead and get started with this lecture video on temperature. Temperature is an important concept in this unit and in chemistry in general. So let's first look at the definition of temperature. Temperature measures the average kinetic energy of a system. Now, if you recall from our last lecture video, we defined what kinetic energy is. Kinetic energy is part of the total energy of the internal energy of a system, and it is kinetic energy that gives atoms, molecules, the energy they need for motion, to move. All right, and of course, temperature is directly measured with a thermometer. In chemistry, the temperature measurements are either in degrees Celsius or in absolute temperature scale, which we call the Kelvin scale. We can look at the direct relationship between Celsius and Kelvin through this equation here. Kelvin is equal to degrees Celsius plus 273. It is important that you memorize this equation and use it for temperature conversions. Why is the Kelvin scale so important? Well, Kelvin is proportional or directly proportional to the average kinetic energy. If the average kinetic energy doubles, then the Kelvin temperature also doubles. For instance, let's look at 0 Kelvin. At 0 Kelvin, the average kinetic energy is also 0, and therefore all atoms and molecules have no motion. Sometimes we'll refer to 0 Kelvin as absolute zero, because there's absolutely no motion that is occurring with atoms and molecules. All right, so what else is important about temperature is to kind of focus on what we mean by average kinetic energy. Now, you got to make sense of this, that when you're looking at a system, we're looking at hundreds, if not trillions, of atoms or molecules, particles in general, in the system. So not all of the atoms or molecules in a system are going to have identical amounts of kinetic energy. Individual atoms and molecules that make up a system are going to transfer kinetic energy between themselves as they interact with each other and their surrounding environment. And this should make sense to you because atoms and molecules are always going to be in constant motion as long as they have energy, and they're going to be bouncing off of each other and crashing and colliding, and therefore this creates transfers of energy. Now, the distribution of kinetic energy of a system can be represented by a very important type of curve called a Maxwell-Boltzmann distribution curve. And we're going to spend the rest of this lecture video on looking at Maxwell-Boltzmann distribution curves. We're going to take the time to draw one here, and it is critical that you're able to do three things. One is to recognize a Maxwell-Boltzmann distribution curve when you see one. Two, to be able to interpret it. And three, to actually be able to draw a Maxwell-Boltzmann distribution curve. All right. So what we're going to do to start off with, we need to essentially draw in our axes here, and I'm going to try to do this with a straight line as possible. All right, and then we got to label our axes, and so on the x-axis we're going to label kinetic energy. All right, and then of course on the y-axis, or we need to label our y-axis, and we're going to do so, we'll label it the number of particles. And really this is the total number of particles that the system has or contains. Okay, and we're just using the generic word particle to represent could represent number of atoms or the total number of molecules that's found in a particular system. So on the IB or AP exam, instead of the number of particles, it may say the number of molecules or the total number of atoms that the system has that we're looking at. Okay? All right, so with our curve, I'm going to actually end up drawing two curves at two different temperatures. So this would be our first curve, like so. And we'll say that this curve represents a temperature of 300 Kelvin. All right? Now, the maximum peak here represents the highest number of concentrated particles. And so at that peak, this is also represents the average kinetic energy. So I'm going to put a little dotted line there. And so at this point here, that represents really the average kinetic energy of this system. All right, and so that's where that's going to determine our temperature, which in this case represents 300 Kelvin. All right. So now let's use look at a different temperature, and let's increase the temperature and see what the curve will look at with a higher temperature. All right. So we'll call this temperature, we'll say it represents 1,000 Kelvin. Now notice what happens when we increase the temperature. The curve is going to flatten out a little bit, and the peak shrinks down, as well as you'll notice that the average kinetic energy of our system also increases, which should make sense, because if our temperature is going to increase, so should the average kinetic energy, since temperature does that very thing. It measures the average kinetic energy of our system. And so I'm actually going to put that in there, average kinetic energy. All right. So you can see that when at two different temperatures, the curves are going to look different. At a higher temperature, the curve flattens out, the average kinetic energy increases, and really what you'll see is that at a higher temperatures, the molecules, or the atoms or particles in general, there's going to be more of them that has a greater amount of energy. And that's what this curve is really showing you, that at higher temperatures there's going to be a higher fraction or percentage of molecules with a greater amount of energy. All right? So let me say that one more time, because that's really important. As the temperature increases of a system, the particles that make up that system are going to have a greater amount of kinetic energy. And so that shows why there's a flattened distribution in our curve. All right? So that's a Maxwell-Boltzmann's distribution curve. So study them, know them very well, be able to draw them like I said, and really that's it for this lecture video.